He also runs UN program. His research examines war and political violence, nonviolence, and conflict resolution. Currently, he is working on a project to evaluate the effect of climate change on terrorism and political violence, and I'm looking forward to hearing his talk.
Make sure you can hear me. Good, okay. And Zoom people, are we good there?
Maybe a little bit louder.
Okay, okay, all right. Question?
Could you take your mask off, please?
Okay, I didn't know if that was allowed, but is that okay?
Yeah.
All right. It'll make it easier. It'll help me with the glasses fogging up. I still have to see. Okay. Oh, wow. Well, thanks for coming out on a cold Saturday morning. I thought everybody would stay home and watch on the computer. And you know, my talk is on climate change, and I almost thought about putting a comma there. Climate change. Come on, it's so cold. I am going to talk about a little bit of the science of climate change and how it works, just because this is something I teach a lot, and I find that students have a vague sense of how it works, but it's helpful if we all kind of understand that part of it. And then we'll get to the politics of climate change and what's likely to happen in the next couple of decades or so. And normally I don't like to use technology here, but I thought since we're doing Zoom and wonderful new facility, I'd give it a try. Was that on?
Hello. There. I knew that. Well, that's why she needs a mask.
Okay. Anyway, I'll get to the politics, but I'm going to focus a little more on the international politics. We'll talk a bit about the US, and I'll try to leave time for questions. If you can't, I hope we can see the screen here okay. There are some pictures just to kind of walk us through some of this stuff. And I guess the prognosis is we're really kind of on the edge here, and it's going to be touch and go about whether we do well with this or not, as far as the globe and climate. Now I'm trying to get this to click. Okay, there we go. So the reading for this week, if you looked at it, was a little disappointing to me. I think we kind of went through all of the extreme weather we had in the last year or two, and events and fires and floods. I think everybody kind of knows about that stuff. I've been here in Bowling Green for 31 years, 32 years, and I keep wondering when we're going to finally get warmer weather. And I found these wonderful, EPA had these maps, and they didn't have Ohio, but what they did was they took projections about climate change and said, well, what's the weather going to be like in Illinois or Michigan, you know, relative to today in say 20 years? And mid-century, so I got Michigan. If you look under Michigan, so we'll be at, Kentucky, Tennessee kind of weather in the next decade, probably. And then we might get down toward Arkansas, Louisiana. I'm not a fan of it. This is the point. But yeah, it's getting warmer. There's, a picture of glaciers changing the Glacier National Park. There's all kinds of evidence. There's no question it's getting warmer. But, we still have a lot of skepticism among segments of the population that it's even happening, or that this is a process or a problem that we need to deal with. And so, there are arguments on those sides, and it's true, the Earth's climate always does fluctuate. So it's still on. It says L. It's L means low.
All right. When did I just eat it? And really, I don't know, we'll always do this.
Anyway, so yeah, the Earth's climate does always fluctuate. We've got great evidence of that. it was cold, well, something was cold last week, it's cold right now. It does still get cold. And, there are folks who say, look, this is bigger than human beings. And it's awful. I can speak loudly, I'm just worried about the Zoom people. Can they hear me? Because I can't tell.
Turn it on too.
Oh, it's okay.
Adjustment there?
Yep, I just, it's all the way up.
It's off. Now it's just flashing. Stop. Now it's on. It's strange.
Mark, we're just doing this to test your patience.
I'm good.
You don't have students, here with us today, so what can we do with students?
Okay. Set it down. One. Wait, whatever. One. Okay. I'm gonna hold it. Okay.
Just changed it.
So,
No, that's just changed it. That's changed.
uh,
I changed number 2. I changed this one. That's
I'm fortunate to be with an audience that would remember that back in the 1970s, when we had the blizzard 78 and all that, everyone was talking about another ice age. So for a long time, people were like, well, it's gonna get too cold, now it's getting too hot, what's going on? We don't really have enough data. These climate models are really kind of a good guess, but who knows? And it's too complex, we really can't understand it. And heck, a few degrees warmer won't matter because we've got air conditioning and other technology to deal with it. And, there's some truth in all of this stuff, but I think understanding the sort of basic science, which many people may already understand, will kind of help us figure out how things are going on. And I think we all kind of know, at least in general, why the sun warms up the earth, but that it really works a lot better if you have a nice atmosphere. And the Earth's atmosphere acts like a blanket, and this thing's off again. I'm just gonna yell, but I guess, how about if I move closer to the computer, would that help?
Whatever you're comfortable with.
Okay, let's do that. There we go. Okay. So, the Earth's atmosphere acts like a blanket, and certain gases in the atmosphere, particularly carbon dioxide and methane, are the ones that retain heat. So the sun comes down, it bounces up off the Earth, but it retains more heat. And we know this because, for instance, this is why Venus is so much hotter than Earth, not just that it's closer to the sun, but its atmosphere is 98% carbon dioxide. So there are greenhouse gases, that retain heat. The main ones are carbon dioxide, methane, nitrous oxides, and chlorofluorocarbons, which is the only sort of man-made gas that's not naturally occurring. And that's the thing that we use in Freon. Think about coolants, that's sort of the main source of that. It's a really tiny fraction of what's in the atmosphere, but each molecule does hold quite a bit of heat. Anyway, when we get, we understand that a lot of this is all still natural, right? Carbon dioxide comes not just from burning fossil fuels, but from decaying of any kind of organic matter, leaves and stuff. Methane, swamps, we're in the Great Black Swamp, it's going to produce a lot of methane, right? Nitrous oxides are mainly coming from fertilizer and agricultural use, but there's some other sources there as well. What we want to do, though, is think about, okay, so the theory here is if there is this thing called climate change, it's driven by the fact that we're burning for the last 150 years or so, lots of stuff that was made by dinosaurs decaying into oil, coal, and gas, fossil fuel, that have been trapped in the earth for millions and millions of years, and we're taking that out and burning it and putting that CO2 up in the atmosphere. Right, that extra CO2 is warming us up. That's, people thought of this back as early as like the late 1800s, that could be happening.
Didn't really start looking into it until in the late 1950s. But it, you know, it's a possibility. And are we back?
I think so.
Okay, well, we've got some more volume there, hopefully. So, you know, we can't just assume that this happens. We have to actually test it. Unfortunately, there's tons of scientists in all kinds of fields that do this stuff. So we want to say, well, first of all, are the greenhouse gases actually increasing in the atmosphere? Because there is a thing called the carbon cycle where, you know, CO2 lasts about 100 years or so in the atmosphere, but it eventually comes back and goes into trees and rocks and soil. And so who knows, maybe the earth can just absorb this extra stuff. Is the temperature actually increasing globally? And if so, is this increase unusual or alarming compared to other sources? And that's the thing number 3 gets at is, so what's the contribution of greenhouse gas compared to the other sources of warming? So I'm going to try to click along here. And I wanted to, oh boy, give you a sense, and some of this may be too small to see, but that if you look at the general shape of that curve, it's going from, you know, you can see it in the about 1850 is the first time we start burning a lot of oil, I guess, and goes up in a kind of an exponential growth curve, which we're getting familiar with this darn pandemic, to today. And it does list some of the countries and regions that produce the annual CO2 emissions from fossil fuel. And so I thought I would show you that just pictorially to make us understand that, first of all, the United States is a major contributor. You can't see it too well on this. I was hoping to make it bigger, but we account for about, here it says 18%. I think that current data is down to almost like around 15 to 16% of global emissions. And China is about 27% of global emissions. The European Union about 9.8%. So again, what's interesting about climate change when we get into the politics is that you know, there's no one country that's the problem. And in fact, what we do in the United States will have a big impact, but it is not the be all end all of the solution. You know, we're only at 1/6 of the emissions are coming from here. And, you know, almost twice that from China, and, you know, Asia in general. And that makes sense, that's where more people are too. So, okay. Let's see, this one, just trying to show you where our emissions levels are. I don't know, again, if you can see, but this is adding up all the major greenhouse gases that are being measured and showing that around 2007 or so, the growth, at least in the US, kind of peaked. And we've been on a downward trend since then with some ups and downs. That's not true globally in every country, but that's where the US is. So when we started seriously measuring this back, Charles Keeling and folks back around 1958 went out to Hawaii to this weather station on the top of a volcano in Mauna Loa and started to measure atmospheric carbon dioxide on a constant basis. And they kept really good records. And there's the little sawtooth curve that shows that it's been going up from around a little under 320 up to where we are today. And I did check the other day, there's a nice, you can check this on the internet. It's 418.09. I mean, they get very precise measurements. And it's a good place to measure because Hawaii is out in the middle of the ocean. And
Yes.
it is? Okay, good. And so there's not a lot of local air pollution to mess it up. And they kept really good records, and there are other places in the world that do this too. You can see that in the last year, we've gone up about 2.5 parts per million. Okay, so what accounts for this up and down cycle every year? The sawtooth part of the graph. Why is CO2 in the air higher in the fall and winter, like right now, and lower in the spring and summer? I bet someone here could tell me.
trees.
Trees, yeah, well, that's the way I think about it, right? So there's probably more deciduous trees in the northern hemisphere than the southern hemisphere. And what happens to trees in the fall and winter? They drop their leaves, the leaves rot, they release their CO2 and methane and stuff. And in the spring and summer, especially the spring, they suck a lot of CO2 out of the atmosphere so they can grow new leaves. So we get the up and down cycle, but the overall trend is going up. And the problem that we face, of course, is that the overall trend is also going up for nitrous oxides and methane. Chlorofluorocarbons, there's a bit of a success story there, at least the top two, and if you can even see that. Whoops, I didn't click ahead, sorry. Look, I'm not coordinating my screen with here. I'm just going to start over. Okay. So the CF, oh, thank you. The blue and red CFC lines are down because back in 1987, we had an international agreement. And you might vaguely remember the term ozone hole. Chlorofluorocarbons also eat away at the ozone in the atmosphere, which is the thing that allows more ultraviolet rays in and causes skin cancer and stuff. So back in 87, there was a big global agreement to kind of switch to other coolants. And some of those still trap heat, but less than the CFC 12 and 11. So we substituted and it's gone down. The ozone hole you don't hear about anymore, but we're worried more about climate change. So anyway, the answer to our first question is yes, greenhouse gases are certainly rising. And so now we want to look at whether global average temperature is actually increasing or not. And this is a graph. Again, if you don't like graphs, just listen to me, but you can see that what they did is from 1880 to about 2020, you've got the departure from the average. This just makes it look a little easier to see when it's warmer and colder. Looks like there was a warm spell there around World War II. And then you see a few cold spikes down in the 70s, which I remember, and I guess in the 60s. Remember, this is global stuff, but pretty much since 1980, it's just gotten warmer and pretty consistently warmer. And there's lots of stuff you hear in the news about. Pretty much every year, they're like, this was the warmest year on record. I think 2019 was second. 2020 kind of came in tied for second. But, I think it's 18 or 19 out of the top 20 years on record have come since the turn of the century. Yeah, we have had some cold winters, but, that's really what the data shows globally. There are many, many different data sets that take global temperature readings and this is not an easy thing to do. You have to get not just land-based, but water and all kinds of things to get global average temperatures. And the temperature readings are pretty accurate, and the data usually pretty much agree. And so this is just a graph to combine a whole bunch of these data sets, 5 of them, I guess, to show you how that works. I want to stress the point about global average temperature. I have had a hard time. Remember, it was February of 2015. Everything before COVID is really blurry to me, but it was cold, and we had this snow that stayed through March. I mean, you remember this? Kids had 17 snow days, and I think that's when we invented blizzard bags. I don't know. It was tough. But if you look at, they compile the global average temperature and put it in color code here. You know that big dark blue spot by Lake Erie. It just reminds me that year it just happened that where we are happened to be really, really colder than average. In fact, record cold. But the rest of the earth looks pretty red. There was only a few other spots that are blue, and that's the colder than average and warmer than average. So globally, when you average things out, it can be cold where you are, but it's still warm for the rest of the globe. Let's see, which one is this? This is, I guess the most recent one I pulled up was the 2019, just to show you again that This is the average that they're saying, you know, basing the color code on, I think is the, it doesn't say, I'm guessing normally it's 1980 to 2000 average. So it's just warmer almost everywhere now. And that's the way the maps tend to look. Why is that going the wrong way? Okay, well, I guess then the answer to the second question, so we know greenhouse gases are increasing exponentially. We also know that for the last, 40 years or so, global temperatures have been increasing as well. And it's getting close to, depending on where you are or what time you take the measurement, 1.2 degrees Celsius higher than the global average temperature around 1880 when these data started happening. But really, we're going to be scientific about it. 40 years is not climate change. It does seem like a lot, 40 years is a long time, but there are many other factors that can cause changes in our average temperatures and weather patterns. And what we have to do is say, okay, how much are the greenhouse gases contributing to the warm up versus some other things, right? Like it's, okay, I had, a donut today, and then I ate some other things, and then tomorrow I'm heavier. Okay, how much did my donut contribute to that? Or was it, the 32-ounce steak I had for dinner? In other words, there's other things that could contribute, right? And that's what we have to do in science, is to try to figure out what are those factors. And I'm not going to go into the details on this so much, but this is just to give you an idea of the kinds of things that could influence climate over decades. And these are hints, so am I off again?
Yeah.
It says one. Oh, it has a red light on it. Maybe there's something about me. Oh, that's nice.
No, we have the same problem last week.
Really? Okay. They've got one of the best webcams here, I gotta say. We don't have those at the university, so it's just the mics. Anyway, thank you for bearing with me. And put your hand in your ear if you're not hearing me, because I know this is a big room and there's echoes and things. So what do you think? What are these pictures? Does anybody know about how these pictures tell you about a factor that could affect weather patterns over decades or so periods? What do you see up there? The one on the left is the sun. This thing has a laser pointer, but I'm not going to use it. Then there's a picture of a globe like I have on my desk. And then there's a volcano, and then there's clouds. Well, let's start with the volcano, right? When we have big volcanic eruptions, what happens globally to the climate? Does anybody know? Ash goes into the air, that's right.
Lowers the albedo.
It lowers or I guess increases the reflection of sun, or reflection of heat, right? And it's actually the sulfur content of a lot of this, in addition to the ash and the soot, which can, reflect sunlight or keep it from being retained. The sulfur that's kicked up from volcanoes, and it has to be a really big volcanic eruption. But if you have a lot of little ones or some really big ones in a year or two, you can have major effects. I think there was a period back in the Middle Ages, like around 537, where they had like 2 years where it was really like so cloudy and over Europe and Asia, at least at the time, we didn't know what was happening in the Americas, and they had failed crops and famines and just horrible things. There's also, I think it was 1813 and 14, after a volcanic eruption in Southeast Asia the year before, they called it the year without summer in the Americas because it was just so cold. So volcanoes have a cooling effect, and if you have a lot of activity, that can change things. The sun on the far left, that's my internet picture of sunspots. I guess the bright parts are sunspots, but apparently the amount of solar flaring and sunspots that we record has a correlation with how much heat the sun is putting out, which we assume is constant, but it's not. And apparently there's an 11-year cycle that correlates with the sunspot, so that it peaks, like the sun has hotter radiation at the peak of that 11-year cycle than at the bottom. And so, you know, the sun could be getting hotter and stuff, right? Clouds are something that's more complex. Really high cirrus clouds tend to retain heat and make it warmer, but low clouds will reflect it. And so as the climate does heat up, the question is, what effect will the clouds have? That's partly because we don't know if we're going to get a lot of low cumulus clouds or a lot of high cirrus clouds, and that's dependent on lots of other factors. So the globe on the table thing, I just threw out because something we all kind of grew up with, I think, at least in grade schools and stuff. But I always wondered as a kid, why don't they straighten that thing out? You know, it's crooked. Does anybody know why all the globes on the tables are crooked like that? Yeah.
It's tipped at 23. If it was not tipped, we would not have summer and winter.
Right. I guess the spin of the Earth, the axis relative to the sun, is tilted at somewhere between 22.5 and 23 degrees, and it spins like a top. And just like when you spin a top for your kid, you know, it can get a little wobble in the spin. And so periodically the tilt of the Earth shifts on that axis, it wobbles a little bit. And in addition, the actual orbit of the Earth around the sun is not a perfect, well, we know it's elliptical, but then even that ellipse shifts a little bit. And depending on how those things shift in cycles of around 100,000 years for the orbit and 44,000 years for the tilt, we can get warmer or colder quite a bit because of our relative position to the sun. I'm not giving you data on that, but that's what causes our ice ages, mainly. So the thing we have to do is we need a lot more than 40 years of temperature data to evaluate what's going on. And that's partly because we know all these other factors, and I haven't even mentioned things like El Nino, which is a cycle that's usually it's a little more short-term, a couple of years, but it does affect warming and cooling global temperatures. Also, just the deep ocean current, which for my students at least, and if you have grandkids, you probably know the movie Finding Nemo. There's a great scene in there where they like are in a hurry to get somewhere and they decide to take the East Australian current. You guys remember this? And the fish are flowing, and they jump in. There's this really fast-moving river of water deep in the ocean and take whoosh back to Australia. That's a global phenomenon, and that takes water that, you know, kind of wells up and goes down to the bottom and races around all around the globe, and is one of the things that returns warm water up toward Europe, which is why their latitude is around, if you cut across and you look at Europe is around where Canada is, but it's way warmer in Europe because of the Gulf Stream and this cycle. Well, that global current in the ocean pulls in a lot of CO2 and moves a lot of heat around, and so the speed of that really can affect global climate as well. So if we're going to account for the impact of just the greenhouse gases, we have to kind of control for all these other factors. And the only way we can do that is by getting lots and lots of years of data about global temperature and lots of years of data about CO2 levels and compare. So how do you get temperature from before 1880? Well, you could look at tree rings and coral reefs, that's the middle one. The main thing that we've done is to get ice cores. And in fact, they go down to Antarctica and in Greenland and drill down into the ice. And because that ice has been there a long time, every year the snow comes and packs down what was before, and you get thousands and thousands of years of historical record, kind of like the tree ring idea. And if you just go down deeper, you're going further in the past. And when you pull it up, you get a nice chunk of ice there, like the guy with the rubber gloves. And in those chunks of ice, oops, in those chunks of ice, there are, you can date it by how deep it was. And it's pretty easy to cut open a chunk of ice, melt it, and in that ice you would have a gas that was trapped when the snow froze, right? And that would be the atmosphere of the time when it froze. And so it's pretty easy to take whatever gas comes out and measure the level of carbon dioxide. So that's pretty straightforward. The hard part, in fact, and we do have people even at BGSU who I have, well, friend Kurt Panner, who does research in Antarctica. I don't know that he's ever dug up the ice cores, but he's been down there with the people doing it. At any rate, it's cold work, but somebody's got to do it. The other thing that's interesting is that there's a chemical property of hydrogen and oxygen. There are different isotopes of hydrogen and oxygen. You probably heard of things like heavy water and stuff. Hydrogen normally is one atomic number, one proton, one electron. But there are isotopes where there's a neutron in there, and so it's H2 or H3. Oxygen also is normally 16, but there's an 18 isotope. It turns out that the ratio of the isotopes of hydrogen and oxygen correlates really strongly with the ambient temperature at the time. So that's how they get the global average temperature thousands and thousands of years ago. And again, this is not just one spot in Antarctica that they're digging this stuff up. It's Antarctica and Greenland, and they correlate it with tree rings and other kinds of things that last 1,000 years or so. And what they end up getting is graphs that could show back 425,000 years what the Earth's temperature was at the time, and that's how we figured out about ice ages, right? And you can see that there's about a 100,000 year cycle or so when the orbit and tilt changes are in the right direction and throws us into an ice age, and that's the blue lines, right? And then there's also been some times when we've kind of peaked and gone, so the ice ages go down, 5 to 10, well, not quite 10, 5 to 9 degrees Celsius cooler than the sort of quote normal. And then the hot house Earth periods, again, which we verify through things like, different kinds of fossils, stuff that we find and data, and, how was that growing here at that time? Well, it was a hot Earth. And so there's this cycle of ice age and hot house Earth. We've been lucky enough to have human civilization evolve during a period when we've been relatively stable at global temperature. But the main thing that they're able to do with these kind of graphs, and this is just, you can't really see it here to really know, but what they're trying to do is correlate the temperature change and the CO2 level change. And what's interesting is that even with all the other factors that affect climate, like the volcanoes, the sunspots, even the orbit tilt changes, carbon dioxide levels really strongly correlate with global temperature. And again, they use statistics and other analysis to prove this, but the change in CO2 precedes the change in temperature. So there is a cause and effect, there is correlation there. It's not the temperature that, because there is some feedback of that when it's warmer, you get different levels of CO2. Okay. So again, I'm sorry about all the graphs, and I know they're not all visible, but just some people like to look at shapes. The one on the left here is actually the more interesting one. I just, because those were 425,000 years, it's hard to see, but this goes back about 15,000 years, which is roughly the time when human civilizations are forming. And so CO2 levels were between 200 and 250 early on, and we get up to about 7,000, 8,000 years ago. They pretty much stay stable between 250 and 300 until today, and that's where you get this big, they call it the hockey stick, because if you turn this sideways. Hockey fans, BGSU. This is the one that goes back 800,000 years. You can see there again, it does vary because of hot and ice age periods some, but This is the CO2 levels. And again, we've always been between about 200 and 300. Well, now we're at about 418, 419. So it's a pretty significant change from the past. Where are we going in the future? Well, back in 1992, the United Nations had a big conference called the Earth Summit, where they decided at that time it was getting a little warmer, and there were scientists saying, "Oh, could be bad, could be bad." So the UN, being the relatively conservative club of governments that it is, said, "Well, I'll tell you what, we will monitor the situation." So they decided to get a very well organized group of scientists, hundreds and hundreds of scientists together every few years to pore over all the new data that was coming out to see what was happening with the climate. And they issued these reports. The group's called the IPCC, which is the Intergovernmental Panel on Climate Change. And they look at the data and they say, here's our best estimates as to what's happened and what is going on in the future. They have climate models that break the Earth on a computer into 1 by 1 kilometer chunks that start at the ground level and go up about 10 miles. They program in all the different interactions, meaning all the chemicals and winds and all kinds of, it's just amazing. As computing speeds have increased, these models have become incredibly accurate at predicting the past. So what they do is they try to figure out what they think is happening with the weather. They make their model and then they say, okay, can that model predict what happened the last 100 years with the temperature that we know happened? When it gets good at that, then they run it forward in the future. And they run it forward in the future, they have to have some scenarios because we don't know how much carbon dioxide will be in the atmosphere. So they say, suppose we have this much, suppose we have that much. And so they run different scenarios. And so there's always a range of outcomes, but if you can see, this graph is showing that by the end of the century, we could be roughly at a range of, if we're really lucky, 1.5 degrees above the pre-industrial temperature level, or if we're not so lucky, around 5 degrees. Depends on the scenario, depends on how much CO2 we emit or how we change. And I'm not even going to get into the sea level rise stuff. I know there's a lot there, but you know, I'm running out of time. So you're tired of the science, I bet. But that's the problem, is we're going to be moving up in temperature. And the key here is that, can our global politics move fast enough to avoid disasters that we think are coming, a flavor of which you get from the reading about all the fires and floods and difficult things there? And my answer is going to be probably not, but we can cheat. And this gets me to the Paris Agreement. So since that 1992 conference, the countries of the world have decided to monitor climate change, have been meeting every year and trying to work on treaties because they wanted to get countries of the world that were burning lots of fossil fuels to cut back on that somehow and start using renewables or whatever, and stop the increase, because it's still exponentially increasing, how much CO2 we're putting into the atmosphere from fossil fuels. Okay, well, there was a problem globally because the rich countries that industrialized first and burned the most fossil fuel that was causing the warming at the time were kind of like, okay, well, we'll try, we'll do this, but we want everybody to participate. It is a global problem, right? And poor countries are like, wait a minute, you caused this problem. We were poor. We've been living in mud huts and, burning wood, which doesn't, by the way, contribute to climate change. Just so you want to have your fireplaces on tonight or whatever. I mean, if it's gas, yeah, but if it's wood, you know why wood doesn't, like if you burn wood, it doesn't make more CO2 in the atmosphere? It does put it in, but the thing is, when the tree grew, it sucked it out. So you're just putting back in what was already there. So you can feel good about fire. I'm just, it's cold outside, people. I just, So the poor countries are like, look, we're too poor. We've got some coal and we want to burn it because that's how you industrialize. We're not going to change unless you pay us. And the rich countries are like, well, no. And even among the rich countries are like, well, who wants to be the first to try to change their whole economy around? That could be costly. So it was really hard to get countries to agree on doing anything. In Kyoto in 1997, they came up with an agreement that just, it was a really low ambition, cut about 5% of your greenhouse gases by 6 years later, even if everybody had kept to the agreement. And it turns out they weren't too bad. It wouldn't have made much of a difference. But the key thing that happened between 1997 and today, or 2015, was that the growth of China and India, and Southeast Asian countries' economies meant that somewhere around 2015, globally, the poorer countries collectively produce more CO2 emissions than the rich countries. So as we moved on in time, China, which is, as I started this, is 27, 28% of all emissions come from China. And that's because they burn a lot of coal, because they got a lot of coal and it's cheaper, right? That's why we're continuing to escalate how much greenhouse gas we put in the atmosphere, right? So they've debated every year at these meetings, the annual climate meetings, how are we going to fix this? What are we going to do? Nobody could agree on who should cut how much, when, and how. And then somebody around 2009, after a particularly bad summit meeting in Copenhagen, somebody came up with a new idea. They said, you know what? It's too bad they're not from the Midwest and the US, because this would be a great story. It's like, but we know potlucks here, don't we? You guys go to potluck dinners. Potlucks are the most amazing miracle invention of the Midwest humanity. I've got pictures of the typical things I would bring to a potluck. You can see that on a good day, I might bake a casserole. And on a not so good day, I might go out to KFC and just come in with a bucket of chicken. There's always a bucket of chicken at these. Do you notice that? Right? And it goes like that, right? Or if I'm really behind and poor, I might just bring a bag of chips. But everybody brings something to the table. And what happens? Have you ever been to a potluck where you run out of food?
No.
No. People, maybe it's just us, it's our culture, whatever, but so they basically came up with the idea in Paris to say, you know what we're going to do? We're just going to let every country bring to the table what they want. Okay. So the idea was, hey, we got to fix the global climate. You're all members of the globe. What are you going to do to cut your CO2 emissions, to also do things like keep your forests from being cut down and other things that will help reduce CO2. Right? And they came to this wonderful agreement. Eventually, literally all the countries of the world signed in. The US did pull out under Donald Trump. Officially, that became legal in November 2020, but then Biden jumped back in after he was elected. So everybody's in. And it's a potluck, or pass the hat or a pledge drive, whatever model you want. I just like the potluck analogy. And the idea is everybody publishes their plan. So you make your plan, you say, here's what we're contributing, here's what we're bringing. But you publish it, it's all online, UN web pages and stuff. And you say, this is what we're going to do, and here's how much CO2 we're going to cut by what year. Everybody just picks their own. If you write up a plan, this is why I never understood why, at least other than politically, but logically, why the US even had support in the population, let alone at the presidential level, pull out. It's like, okay, Obama submitted a plan, but if you don't like the plan, you don't have to pull out a whole treaty, you just submit another plan. I mean, nobody's going to care. It's like, when you say, well, this president said we were going to bring a casserole, and that's way too much work and too costly, so I'm going to bring back potato chips. Well, fine, bring potato chips. All you have to do is just publish a new plan. It's not a big deal. Anyway. So that's how the Paris Agreement works. And what they do is, okay. Now I'm not getting that. There, whoop, there we go, whoops. So then what we get is, it's all, I mean, why is it we don't run out of food at the potlucks? Because everybody brings too much, right? Why does everybody bring too much? Well, not just because they don't want to run out, right?
I think it's human nature, because then when they look at it's human nature to not want something without something, you know?
Well, you want it to be a fun party and all this, but if everybody brought potato chips, we'd have a problem, right? But has that ever happened to you? I mean, even when I was a poor college student, I didn't have that problem at potlucks. People would bring more. I think part of it is this sort of social pressure to not look like you're being unkind and ungenerous, right? You'll get called out if you keep coming every time. Oh, there's Mark, he's coming with potato chips again. Okay. Thanks, Mark.
You can't cook.
Yeah. Well, if you can't cook, go to KFC, right? Anyway, so the plan is that, we have this Paris Agreement 2015 and 2020, which they had to put off a year because of the pandemic. And every 5 years or so, you're supposed to update your plan. So it's kind of a new potluck. It's like, okay, we know what you brought last time. Give us a new plan, because every year we're looking at the new science, figuring out how, if it's getting better or worse, and what do we need to do. So every 5 years, you update your plan. In between, you have meetings where they do this global stock take, like, oh, how's the plan working? Are people actually obeying what they said? Because it's a pledge. And the goal is to get to zero emissions globally by 2050. So that's the goal, and it's all based on name and shame. It's voluntary, and you just look bad if you don't do your part. Yeah.
What does it mean net zero? I mean, we're still emitting, but
Yeah.
we're doing.
Thank you, because that word net now is associated with the internet. What this means is that we'll still be burning fossil fuel in 2050, but maybe we will have planted more trees or trapped more CO2 in the soil from new farming methods or improved farming methods. Or there's lots of ways that we can add to how much CO2 we pull out of the atmosphere. So the idea is that instead of that exponential growth curve in CO2 emissions every year, it will be flat. Like, we're not going to be adding more than we take out. That's the goal. The United States initial plan under Obama was to get from, it's tons of CO2 per year, whatever. So you can see we kind of were going up and up and up. At least for just CO2, we peaked a little after 2000. There was another bump in 2007. Obama said by 2025, we want to get to 26 to 28% below 2005 levels. So it was a 20-year thing. We'll drop down to here. Pretty much stayed on this path. I think I have a slide coming up to show you some ripples, but had we done nothing, this gray line is where we would have gone, right? So that's business as usual. So going down and by 2020, we were actually not too far off the path, but we needed some acceleration to get there by 2025. Then what happened was that Biden decided just last few months ago, really, as part of this is going to be in the Build Back Better, but some of it's in the infrastructure plan too, to really increase the amount of climate spending that we're having, and also do a lot of infrastructure changes to promote job growth. And that his goal now is, let's take 5 years out, it will be more like 50 to 52% below 2005 levels in 2030. You see, you got to get there before you get to zero in 2050, so it's tough. So where are we going here? So if we look at who brought what to Paris and where things are standing now, the problem we have is that had we done nothing, we would be looking at 3 or 4 degrees by the end of the century. The pledges come in at around 2.5 degrees if we add up, if everybody does what they say. And here's where we need to be, which is less than 2 degrees. So, why this thing about 2 degrees? You hear it in the media, they never really explain. It just sounds like a nice round number. But that was one of the things they agreed in Paris, was that we should never go above 2 degrees higher than the pre-industrial levels. And that even 1.5 degrees is kind of shaky because there are feedbacks. You've heard of these things called tipping points, where things are going along, however, they're kind of about the same, and then you hit a tipping point and all of a sudden change habits very fast. All the climate models and the studies that have been done that the UN looks at, makes their estimates on, don't really account for a couple of big problems that are out there as we get warmer. The easiest one to think about would be the permafrost, right? So you've got large, vast swaths of tundra in Russia and Canada that are permanently frozen. They're frozen sometimes hundreds of feet down, right? And they've been that way for thousands of years. But when it warms up, they start to melt. When it melts, lots of methane from all that decaying stuff. In fact, woolly mammoths, and you hear about this, they're finding, all these mammoths are coming up in Russia, bones and tusks and things. I've heard, efforts to let's clone, let's like somehow regenerate them from DNA and woolly mammoths. That'll be fun. What could go wrong, right? We have movies about that. Anyway, as the permafrost melts, more methane goes up from the ground that's been stuck there for thousands of years that hasn't been in the atmosphere. That creates more heat, which makes more permafrost melt, which makes more methane, and so on. The same kind of process happens because there's a lot of methane trapped in the oceans. And there's so much methane down there that if you compare, we have 800 gigatons of CO2 equivalent in the atmosphere now. And we're releasing about 30 to 40 gigatons a year. What happens when we release the hundreds of gigatons in the permafrost, or maybe thousands in the ocean? Where at that point, it won't matter if humanity has no additional emissions. The Earth itself will be warming it up, and we won't be able to do anything about it. The other feedback is a little easier to think about too, and that's the fact that the ice caps reflect sun, and the Arctic ice cap has been shrinking, and it's still there, but it's shrinking, and it reflects sunlight, and as it shrinks, more of the blue water comes in and absorbs more heat, which warms up those oceans and the Earth, which makes it shrink more and more and more. And, it's on that downward path. We're losing about 10% or so every decade. We still have ice up there, but the thinking now is around mid-century, we will have at least summers that are completely ice-free. This has led to a whole boom of speculation about oil and gas drilling, and kind of even some military conflicts about who controls all this Arctic territory that no one cared about before, but that's another story. So anyway, the 2 degrees thing, and this is the kid from Home Alone, do you remember that? Yeah, I pull these slides up for college students thinking they'll know, but I'm glad that you all do too. So past 2 degrees is a tipping point that it's not that it's going to get so much worse right away if we get 2 degrees, because we're already at 1.2. But after that, we won't be able to stop it. It'll be out of our hands. And so that's what's scary about this long term. And it would be a really good idea not to go past 2 degrees, maybe even 1.5. So how are we going to cut back? Well, we did a good job in 2020 because of the pandemic. All we have to do is shut down the economy in our lives and live in horror for a year and look at oil demand drops, energy demand, CO2 emissions. Well, of course, that all stopped in 2021, and the data isn't out yet. I did find the US increased 6.2% after we dropped about the same amount. So then we took a year off, but that didn't matter because in fact, global CO2 levels still went up. They just went up 2.2 parts per million instead of the usual 2.4, 2.5, or something like that. So what are we going to do if we can't get the politics of the potluck and countries to shift fast enough to electric cars and clean renewables and, you know, airplanes? We still can't figure out, honestly, how are we going to get, you know, air fuel, diesel for shipping and other things, so that we aren't putting more CO2 in the atmosphere. How are we going to do this? We're getting close, you know, 1.2 degrees already. The answer is we can cheat. If we get close and it starts getting bad, and the year or so of bad weather and the climate type disasters gets, you know, compounded in 10, 15 years, and people are really having problems. And by the way, those problems won't just be bad weather and fires and floods and things. There'll be things like all of that happening, plus food shortages, because we can't grow food, because unless we adapt in time, you know, rice won't germinate above 94 degrees. China is very, very worried about climate change because they're worried about feeding their people. And they know that if they can't feed their people, the government's not going to be staying in power. And, you know, people have famines, they tend to like try real hard and then flee because there's no food. But if there's no food globally, then we don't have enough food to go around. And nobody's going to want refugees coming into their shores because they're hungry. I think we figured that out already. It's not a real popular thing. We've got, you know, all kinds of problems with people leaving the areas of, you know, the Sahara Desert expanding in Africa, and refugees fleeing not just conflicts, but now climate issues going into Europe, and they're not thrilled with that. U.S. is going to face more of this. The waves we've had so far have to do with political conflict and violence in Central America, but the model suggests that the places that are going to get hit first and worst agriculturally are going to be Central America and those sort of areas. And where are those folks going to go? They're going to go north. So you can have refugee flows, you can have other things that governments failing, political conflicts, revolutions, violence. It could get ugly. So as we get close to that, maybe we'll get the desire to cheat. And so there are some methods to cheat, and we call this stuff geoengineering. There's some really low-tech ways and some really high-tech ways. Like, yeah, we could put like big mirrors up in space to reflect the sun. Let's let the billionaires with the rockets do that one. It's kind of expensive. A cheaper way would be to just put floats out into the ocean and spray mist to get it up a couple hundred meters and create more cloud cover that reflects the sun better. If you do that on a big scale with automated things, that would be pretty easy. You can do stuff to trigger algae blooms in the ocean, not like Erie, which will suck out CO2. You can capture carbon from smokestacks and bury it, although that's really expensive. The other cheapest thing you could do is just put sulfur into airplane fuel and have all the airplanes in the world add to what they're already doing, actually, which is spreading a lot of sulfur high in the atmosphere, which acts like those volcanoes and will reflect heat from the earth. The problem with this, of course, is we don't have a global planetary government to manage global planetary climate management. So who does what? You know, you can also just put sulfur up in a weather balloon and, you know, seed the atmosphere with that. What if every country just does whatever the heck they want? You know, we could cool down too much. And what if we, you know, some of these technologies, we haven't really done much research, we tried it, it doesn't work, or really wrecks food production, or maybe it's great for Bangladesh, but boy, it really made things bad in China because weather is hard to control globally, right? Anyway, we might be able to cheat. That's sort of my final answer there. And I hope we have time, because I know I've gone longer than normal, but you know, I do think big changes are coming. You know, we've seen big changes in our lifetimes with And I guess the internet and cell phones are my two claims to fame. I know I was always jealous of my grandparents who saw, you know, automobiles and radio and TV, and I kept thinking as a kid, when am I gonna get something cool? I want jetpacks. You know? And then lo and behold, in the 90s, there's the internet. I'm like, oh God, this is it. You know, it just wasn't as sudden. The market is working, even if you don't try hard. Rich countries there's all kinds of market as well as political forces that are moving us to renewables and electric cars and all this very quickly. It better speed up because we're not gonna make it time we don't. And we can always try geoengineering, but that may be risky. Depends what side of the bed I wake up each day, but I'm starting to think it's not gonna work out so well. Our children and grandchildren are not gonna have the stable climate that we lived in. And I just hope that we don't really wreck it. Humanity has been survivors. We've made it through, well, I guess if we go back to Neanderthals, at least 100,000 years. We'll make it somehow, the earth will make it, but it could be a shaky half century or so. So I'll stop there and take questions and turn off the PowerPoint if you want, and thank you all for listening.